Hello. Today we'll talk about Maxwell's equations and boundary conditions on which we will apply those Maxwell's equations. Maxwell's equations are a collection of everything else that we have discussed so far. In 1865, Maxwell published a paper where he collected everything that was known about electromagnetics, statics, electrodynamics, and he combined them into a set of 20 equations and 20 variables. Now more commonly, when we hear the words Maxwell's equations, we refer to Oliver Heaviside's restatement of those 20 equations, which are now more compactly described with just the 4 equations that you have probably already seen before. The learning objectives for this lecture is to learn Maxwell's equations and be able to apply them to a range of problems. Before we would look at Gauss's law and apply it, we would look at Biot-Savart and apply it, but now we'll have to have a set of simultaneously existing Maxwell's equations that we will need to make sure are calculated. And we will calculate them on boundaries between different media, and we will evaluate those electromagnetic problems on those boundaries in order to understand what Maxwell's equations mean in terms of charges and currents on those interfaces. As previously stated, Maxwell's equations are a collection of the results we learned previously, but this time we'll also incorporate some of the material properties that were discussed in the previous lecture, lecture 4a. So if we go through the equations, the first one we recognize as the Gauss's law, and it means that the electrical field lines that are leaving a closed surface are proportional to the charge that is enclosed inside. The second Maxwell's equation is similar in the regard to the first. However, because there are no magnetic monopoles, there is no magnetic flux that can exist through a closed surface. The third Maxwell's equation is a restatement of the Faraday's law, where it says that a changing magnetic field can give a rotating electric field. The fourth equation is that of Ampere's law, which relates the current to the magnetic field rotation. However, there was an addition that was brought in by Maxwell, where he added this term, which is similar in a sense to this term, which helps relate the change in electric field to the rotation of the magnetic field. So in a way, those two equations are somewhat symmetric, except, of course, for the presence of this minus sign. And this minus sign is necessary for conservation of energy. These equations are generally true, but we will make a few assumptions about materials very, very often. We will let them be simple, linear, isotropic, and they'll also often be homogeneous. What this implies is that D will be related to E through permittivity, B will be related to H by permeability, and J will be related to E by conductivity. The last one you will recognize as Ohm's law. Returning to the first of Maxwell's equations, we see Gauss's law for electric field. It means that the lines of electric flux must begin and end on charges. And here we have it as divergence of E is equal to rho epsilon. Another way to write it is divergence of D is equal to rho sub F, meaning free charge density. This is an important distinction because the flux will not depend on the bound charges but only on the free charges that exist. The next step is to take that Gauss's law and apply it on an interface. Here, instead of looking at the differential equation form of Maxwell's equations as we had it here, we will look at the integral form, and then we will look at an interface. So above we have media 2, and below we have media 1. What we see here is a Gaussian pillbox which has some volume over which we will integrate this integral, divergence of d. And what we're interested in is the amount of flux. However, what we will do is we will allow this pillbox to shrink, and as we let the height decrease to 0, we quickly realize that some integrals will not contribute anything, and what we end up with is this equation where we have the normal component of d2 and normal component of d1 entering and leaving the surface, multiplied by the area. Now, of course, we know that the area inside will also have a surface charge density which multiplies that A. And if we are to rephrase this in terms of a more independent set of coordinates, we can write this as a dot product between the difference of d2 and d1 being equal to the surface charge density. In essence, it implies that d2 and d1 can be discontinuous, but this discontinuity has to be counted perfectly by the surface charge density. When we look at the second Maxwell's equation, we recognize it to be Gauss's law. But instead of talking about electric flux, we're now talking about magnetic flux. And because there are no magnetic charges, at least we haven't found them, lines of magnetic flux must close on themselves. They don't have an option to end on a monopole. Instead, they will continue making circles, and what that means indirectly is that when you evaluate an integral across a closed surface, the amount of flux in and out will be exactly the same, meaning that there cannot be a magnetic charge enclosed. Now consider what happens with this equation when we evaluate an interface. We will similarly convert the differential form into integral form, and we will look at an interface. And quite similarly, we have our two media up and down with respect to this drawing. We have a similar Gaussian pillbox, but now when we shrink this pillbox down to 0 height, we see that the amount of magnetic charge inside, or magnetic charge on the surface of that circle, is 0. And this gives us boundary condition on the magnetic field, where the dot product of the difference between B2 and B1 has to be 0. And what that means is that the magnetic flux density is continuous, but because we have a potentially different mu above and below the interface, the magnetic field intensity, H, can be discontinuous, but B is always continuous. The third Maxwell's equation is Faraday's law, which relates the voltage induced in a loop to the time-varying flux penetrating that loop. In differential form, we have del cross E, and that is equal to negative dB dt. What this means is that the greater the variation in our magnetic field, the stronger is our induced rotation within the electric field. This minus sign can be figured out from Lenz's law, which means that if you have B field increasing in this direction, it will tend to have current or electric field that will rotate around like this. But in reality, the world resists change, and you need that for conservation of energy. So when we have B being inserted, that means that it has to give the negative of that in order for things to balance out. So when we see this in action, as B changes from side to side in strength, we see electric fields grow and decrease, go in the other direction, and so on. And we see that once B field crosses through here, through the 0, 0 point, that's where dB dt is the greatest. It's the greatest swing. So that's where the electric field will also be the strongest. Now we'll consider how this behaves when we look at a material boundary. And instead of looking at a Gaussian pillbox that rests above and below the interface, we will now have just an area, a loop, that we normally would have to integrate over the entire area. But what we can do with the Stokes theorem is rephrase the calculation to be in terms of the loop, which looks like that. And of course this loop is delta L by h, but in reality we want that integral to be as small as possible, so we'll let that shrink. There. We take the limit as h goes to 0, and then we'll look at the dB dt present within that, and E dot dl. From there we discover that because of the different directions of our loop, because it was going around, E2 tangential component will pick up a positive delta L, and E1 tangential component will pick up a negative delta L, depending on which side you choose to denote as positive. So together we can write the boundary condition as n cross E2 minus E1 is equal to 0, and what that means in words that the tangential component of the electric field at a material must be continuous. And this is denoted with the two arrowheads right here for E1t and E2t being the same. The fourth and final Maxwell's equation is that of Ampere's law. And Ampere's law is usually phrased as del cross H is equal to J, but Maxwell's extension to it included the term dd dt, and that is to account for the charge continuity being a necessary component of all things electromagnetic. When we let a current vary across a capacitor, what will happen is we will have circulating H instead of circulating E like we had in the previous example of Faraday's law. But along with that circulation of H, we also have charge buildup on the capacitor. It will charge and discharge as dictated by this equation. The same kind of factor would have existed in Faraday's law if we had magnetic monopoles. But since we don't have them, the Faraday's law is slightly simpler than is the Ampere's law. When we take Ampere's law, we can apply it in the same way as we applied Faraday's law on an interface of two media, and we'll look at a loop that goes below and above that interface. And instead of calculating or looking at differential equation, we now look at the integral form of that equation. And similarly to before, we don't need to look at the whole area. We can just look at the loop that encircles that area. That means that we look at the boundary alone. And similarly to before, we want to consider the smallest loop possible, and we allow that H to go to 0. And at this point, a lot of things are recognizable from Faraday's law. This term will contribute nothing as before, but we do have this J that's present, and it is denoted on this diagram as the surface current density, which is perpendicular to those red lines and is perpendicular to the normal vector that's extending above from the interface. Evaluating further, what we end up having is a similar positive contribution of delta L to the tangential component of H2, and a negative contribution of delta L to tangential component of H1, and that difference has to be accounted for by the surface current density multiplied by that same delta L. Getting rid of delta L, we can write this final boundary condition which states n cross the difference of H2 and H1 has to be counted by J sub s. In words, this means that H2 and H1 can be discontinuous, but that discontinuity has to be exactly contained within this additional surface current density. The consequence of the Ampere's law is the continuity equation. If we take the divergence of the left-hand side, del cross H, and the right-hand side, J plus dd dt, then we can take advantage of the vector calculus property of divergence of curl of a field being equal to 0. Once we take this term and we spell it out in terms of divergence of J plus ddt of divergence of D, we can recognize this component as being equal to our charge density. And the final result is the divergence of J is equal to negative change within charge density. What this means is that whatever flux of current there is incoming or outgoing out of a closed surface must be exactly accounted for by decreasing or increasing charge density within that surface. Of particular interest is looking at the boundary conditions when dealing with perfect electric conductors that have the property of conductivity being infinite or equivalently resistivity being 0. What this means is that the fields inside the PEC must be identically 0. Now, of course, as you might guess, this is an approximation. However, this approximation is a very good one, and it can often pay dividends in speeding up your simulation by not having to calculate a really, really large conductivity having a very, very small effect on your overall construction that you're trying to simulate. This comes into play when you're simulating circuits, and in circuits you don't have any resistivity on wires, at least it's assumed, and instead they are described as perfect conductors. And when you look at perfect conductors, you can describe things like gold, copper, and aluminium very, very well. A property of that approximation is that when exposed to fields, the charges rearrange themselves so as to create zero field condition. What that means is that there is infinite relaxation, and this results in very particular surface charge and surface currents. When we look at the electric fields with a surface charge density on that interface, we will know that n dotted with the difference of d2 minus d1 is equal to that rho sub s. But since we know that d1 is going to be 0, we know that essentially d2n, the normal component of d2, has to be equal to the surface charge density, and that will also imply that b sub n is equal to 0 for the same kind of consideration as the second Maxwell's equation, the Gauss's law for magnetic monopoles. When we look at the H fields, we will worry about surface currents, and applying this condition of n cross H2 minus H1 is equal to surface charge density. Once again, we can realize that H1 is going to be equal to 0, and as a result, n cross H2 has to be equal to J sub s. What this means is that the magnitude of the tangential component of the H field has to be equal to the magnitude of the surface current density, and the tangential component of the E field has to be equal to 0. And as a result, when we group these four boundary conditions together and evaluate them for PECs, we end up with 4 equations that are much simpler than the ones that we had to consider before. And if you can make a good justification for your circuit element or your simulation component to satisfy those conditions, then you can really speed up your simulations. Finally, as for the tutorial topics, we will look at simple capacitor problems with mixed media to demonstrate normal tangential electric field boundary conditions, and we will relate boundary conditions for the E field to the boundary conditions for the current density.